All right, so this is going to be an introduction to limiting and excess reagents or reactants, which isn't actually a particularly challenging topic on the beginning point. So a limiting and excess reactant is something you're familiar with. Let's say I want to make a marker set that consists of a green, a blue, and a black. Neat. So obviously I need one of each. Or maybe I want to make a marker set that's green, black, black, blue. That makes more sense to me right now. So obviously if I'm trying to make this, I need one of these, two of these, one of these. Great. So if I have another blue marker, even though I'm trying to make this set, this is worthless to me. I don't need this to make this end point. In the same breath, if I need to make, again, blue, black, black, green, if I need to make that, and not only have this, I'm limited by the fact I need another black marker. And you're saying, well, this is obvious stuff. It kind of is. But the game we're playing here is actually really important in real life. So let's say you're planning a trip for, hypothetically 23 students to go to the Tetons, and you need to buy food for 3 weeks and can't stop at a grocery store on the way. You don't want to buy too much of food, and you don't want to have a limiting reagent of, bacon. You want to make sure you have enough bacon. This is a great way of doing this. If you're running a business and you want to make sure you're ordering enough things for your supply and demand to be met, these are the kinds of questions actually that we've shown a lot. And in truth, where you learn how to make sure you're ordering the right number of things, how to deal with excess supply, how to quantify your mistakes, that turns out to be a chemistry question, at least easiest approach by chemistry. And we call this a limiting excess reactant. And so we teach it with chemistry, but this skill actually shows up a lot of places in the world. And I've given you a note sheet, and I'll try to follow along with it. And we're going to look at the reaction between sulfur, as it exists in nature, which is actually S8. So when you have yellow sulfur, it smells like rotten eggs. It's actually S8, and chlorine gas, which is mustard gas, effectively mustard gas. So a very potent reaction, one I'm not just going to go and set up and do. Let's just look at it mathematically. And I'm asking a very practical question. On one hand, I've got 200 grams of sulfur, and on the other hand, I have 100 grams of chlorine, and I combine them, and I want to know exactly how much S2Cl2 is made. And I've got a reaction at the top. S8 plus 4Cl2 yields 4S2Cl2. And I want to know exactly how much is made, and one of these things is going to run out before the other. And so to do this, I'm actually going to set up two parallel stoichiometry questions. So on your worksheet here, I have a box here. And the top box asks me to say, basically, what is the most possible product I could get? Let's say I take the sulfur and I burn it in a room made only of chlorine. One, run because you're dead if you're in that room. But two, if I take that sulfur and I burn it in a room with so much chlorine that the only thing that could possibly run out is sulfur, and we call that excess chlorine, what would happen? And so mathematically, I'm going to set up very quickly a two-step stoichiometry problem to solve for moles of S2Cl2, starting with 200 grams of S8. I'm going to completely ignore the fact that chlorine exists. And this is a thing you already know how to do and are good at. So let's run it really quickly. And I'm set up with something that I'm pretty familiar with how to solve. And I type the calculator, and magic happens, and I get a number. So what happened here is if I ignore chlorine, if I have 200 grams of sulfur, the most I can possibly get under any circumstance is 3.11 moles of S2Cl2. I'm going to do the exact same thing for the second thing, but I'm just going to start with chlorine and ignore the fact sulfur works. I've got so much sulfur. I have a room full of sulfur, and I inject just this 100 grams of chlorine. How much of it reacts and makes moles? So I'm going to set up a completely different stoic problem than the first one I did. So now I'm coming down here to the second box, and I'm going to figure out exactly what that maximum is, ignoring the fact sulfur exists. This answer, and what I do beneath it, we'll put it in a different color to make it more clear, can't talk to each other ever. They're completely independent. They're hypotheticals. Neither of these things happens yet. They're just the best possible case. So I need to set up another stoichiometry equation. So here we go. And that ain't bad, right? One thing to note is that these molar masses, because this is S8 and Cl2, aren't what's on the periodic table. They're the periodic table times, 2 times 8. So I need to do this and get an answer to my calculator. And there we go. I've made two different predictions. One's the prediction for my sulfur, and one's the prediction for chlorine. And frankly, this is a good half of what I'm asking you to do in this problem. And it's really easy because it's just two-step stoic. This is stuff you've been doing for the whole week. Now the question beneath this, down here at the bottom, right? So green is the top box, blue is the second box. The question at the bottom says, what's the excess and limiting reagent? Now in nature, you never get things for free. So clearly, whichever number is smaller is what's going to actually happen. So we call what actually happens the limiting reagent. So this is going to be our limiting reagent. But please note, the limiting reagent isn't the number. Okay, that's a theoretical product. The limiting reagent is what's causing the smaller number to happen. So because this number is smaller, whatever's causing that, in this case chlorine, is called the limiting reagent. Obviously, if one thing's limiting, the other thing is called excess. And again, just like the limiting reagent, it's not 3.11 that's the excess, it's the sulfur that's causing the excess. Now I want to make a point that bites students in the butt often. Just because this number out front is smaller doesn't necessarily mean the product will be smaller. For instance, hydrogen is very light. So if you have 100 grams of hydrogen, you have 50 moles of hydrogen. The odds are 100 grams of hydrogen is never really going to be your limiting reagent unless you're working on things like an industrial scale. On the other hand, 100 grams of chlorine is only a small number of moles, 1.4 moles it turns out. That might actually limit it. It doesn't matter. Nothing over here matters. It's just the answer. The big number is the excess reactant. The little number is the limiting reagent. And you identify what is what by looking at the names that cause those. Not the numbers, the names. So on the bottom, the excess reactant here would be considered S8, and the limiting reagent would be chlorine. So this right here, this is the important thing. This is the thing I need you to understand for lab on Monday or Tuesday. This is not, however, the hard part of this question, but it is the part that's like 60 or 65% of the points on the test. And a question like this, I guarantee will show up on the final. It's not awful. There's one more easy thing before we go on. So on the back, if you flip it over, you'll note that I'm asking you to find the number of moles that actually happened and multiply it by the grams of your product. Because what we've done here is we've actually made a forecast. Okay, this is fantasy world. This doesn't happen, but this does. So if I put these two things together and work on it, when I reach 1.41 moles of S2Cl2, I've run out of chlorine. There's no chlorine left, so there's a hunk of sulfur in the bottom of the material that didn't react. Whatever, that's waste. But we're out of chlorine, and we've made this much product in theory. And if I made this much product, I know how much that should weigh, and I can make a prediction that I can actually measure. Because I can't really measure 1.41 moles of S2Cl2 in any practical way, but I can measure grams. So if I did this reaction like in a container, and then caught all the S2Cl2 and measured the weight, I could figure out if I'm right or wrong. And this is radically different than biology, radically different than anything else you've done in chemistry. This is a measurable quantitative prediction. This is where chemistry starts being chemistry. So what I need to do is take the moles of whatever the limiting reagent theoretical yield is here and multiply it by the molar mass of that to figure out how many grams I'm supposed to get. Well, let's check that really fast. Okay, I need to quickly find the molar mass of S2Cl2. So I need to make a table. So now I know the molar mass of S2Cl2. I can take that and multiply it by the number of moles I want. And because, again, my smaller number, the number that the limiting reagent created, is actually what happens, I'm going to take the 1.41 that I'm predicting happened, I'm going to take that 1.41 mole of S2Cl2 and multiply it by my molar mass. So there are 135 grams in S2Cl2. And I'm going to multiply that by 1 mole of S2Cl2. The moles cancel. I'm left with grams. So I just need to type that in my calculator really quickly. This is just math you did in November. This is just converting moles to grams. It's not hard. All right. So I type it in my calculator and I get this. If I'm right about this, I could go carry out this reaction in lab theoretically, measure it, and know I'm right because I got this number. And in a couple days, I'll actually teach you how to grade how well you did in a lab. For now, I have a measurable prediction. We would get 190 grams of S2Cl2 if I just had 200 grams of sulfur and 100 grams of chlorine and combine them under optimal circumstances. This is really important in chemistry. Okay, I just want to point out what we did here, here, and here is the big point. You're what's called the theoretical yield. The rest of this page isn't going to matter as much. So let's take like a 30-second mental break here and come back to it. And let's look at the harder part of this. The stuff I'm going to ask you to do on Monday or Tuesday in lab, and the stuff I really want to look at on Wednesday in class, is really going to be these steps. And these steps, I just want to point out, aren't anything new. We're just running two problems in parallel and choosing the number that's smaller. As long as we're working with the same reagent, as long as we're looking at the same product, this works out every time. All right, so that little mental break aside, let's go ahead and move on to these bottom boxes here on the sheet. So right now, as far as we've gone, we've made an official prediction. We've made a prediction that 1.41 mole of S2Cl2 form in this reaction, right? And that's real life. But that's not the only question I can ask you. Because I could ask you, well, how much extra sulfur did you have? Remember, we said the chlorine was what was preventing us from going further. So in theory, I'm wasting sulfur here. And so the question I'm going to ask is, well, how many moles of sulfur did I actually need? But if you notice, excuse me, that I have moles here, and I'm looking at sulfurs, I'm asking about how many moles I needed. That's just a one-step stoichiometric problem. So that's easy to set up. Let's do that really fast. And I just set up a two-step stoichiometric like I'm used to. I took my information I was given, which was my prediction of how much product I was going to get, and I just figured out how much sulfur I would need to get that by a one-to-one step here. So if I needed it, I only need 0.35 moles of S8, but I wasn't told how many moles of S8 I had. I was told how many grams I have. So one of the things I need to do here in this big box is figure out, well, how many moles of S8 did I start with? So that's not so hard to do. Let's run another stoichiometric problem. You'll just see this is just stoichiometric problem on stoichiometric problems. So here we go. All right, so I just set it up, right? I knew I had 200 grams of sulfur at the start. I just figured out how many moles that was. So I started with 0.78 mole, but I actually only needed 0.35 mole. This is great news. This is a good sign that I'm doing things right, because I'm saying I needed less of it than I had, right? I'm saying I had 0.78 to work with, and I only used up about half of it, which is a thing in the back of my mind that's checking off the list saying, okay, that's good, because I already guessed that the S8 would be in excess. And so if that's in excess, that's wonderful for me, because I can just subtract things out, right? If I already have this, I had this at the start, and I use this out, it's just a mathematical difference between the two to figure out what I need to do. It's just a simple subtraction problem. This isn't bad. This is about as easy as it gets if you can just do mental math. Now, I'm not quite done, because it's in moles, but I only have to do one more thing left, right? All I have to do is multiply it by the molar mass to figure out how many grams extra I had, right? So if I have this many extra, if I had 0.43 mole extra, all I need to take is the 0.43 mole extra I had, I was trying to say it's mole, and multiply it by the molar mass of sulfur to figure out exactly how many grams it was. 0.43 times 256.8, right? Because that's the molar mass of S8. And we can do that really quickly with the calculator. And that comes out to be like 110.5 grams extra. S8. So if I did this right, if my math is right, what I'm saying is if you ran this reaction in a perfectly sealed container, you would have gotten our theoretical yield of S2Cl2 in addition to having 110 grams of sulfur just sitting there in the bottom that didn't react. So I could have gotten the exact same result by including 110 less grams of sulfur than I did. That's really useful information. I'm trying to make this reaction as efficient as possible, or not trying to waste what's going on. Now, I understand this part is way harder than what we started with, right? This is a little scary. And honestly, it's worth only about 15% of the points on this question. But that's the difference between an A and a B, for instance. So, at this point, we're going to be working on this on Tuesday together in class, but on Monday I'd like to do a lab together, or excuse me, because Martin Luther King Day. Tuesday we'll do a lab together, and Wednesday we'll be working this in math more. But I want to make sure that we have these skills down because we're going to be talking about them in lab on Tuesday. So I hope you have a wonderful 3-day weekend, and I'll see you then.